Welcome to topic 4.2. Here we will introduce the idea of the mole and how we use it to count particles in chemistry. The mole is a difficult idea and students often have problems with it. You will have been told that it's a number, a very large number, so large it's impossible to grasp, and that's true. You'll have heard some analogy like if you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers or something else to that effect. But it's hard to grasp the idea of a mole by just trying to grasp the size of it. A better approach is to explain it in reverse by looking at the problem that the mole solves. Let's start with a simple chemical reaction, the burning of carbon and air to form carbon dioxide. Whenever chemists carry out chemical reactions, they will want to know how much of one reactant to react with another reactant to produce a certain amount of product. This immediately makes it necessary to be able to count particles because, as we've seen, chemical reactions operate at the level of particles. In this reaction, one atom of carbon will react with one molecule of oxygen to form one molecule of carbon dioxide. 2 atoms of carbon will react with 2 molecules of oxygen to form 2 molecules of carbon dioxide. 1,000 atoms of carbon will react with 1,000 molecules of oxygen to form 1,000 molecules of carbon dioxide, and so on. As we saw before, the chemical reaction will give us the ratios at which the particles will react and be produced. So simply put, chemists need to be able to count atoms and particles. There's no other way around it. But of course, not only is counting particles impractical, it's also impossible. What kind of machine could do such a thing? Well, we have the mass balance, but of course this measures mass. And how can you measure particles as small as atoms with this? But if we had a way of easily converting numbers of particles to mass, then we would have a sound approach. For example, if we knew that 1 gram of atoms was 1,000,000 atoms, then we could easily convert between mass, which we can measure in the lab, and the number of particles that mass contains. But there's also a fundamental problem with this approach because, of course, every atom has a different weight, and there are more than 100 naturally occurring elements to deal with. Let's have a look at some examples of elements to see if we can figure out how we could get around this. You can see that our hydrogen atom has a mass of 1, our carbon atom has a mass of 12, and our magnesium atom has a mass of 24. This means that a carbon atom weighs 12 times more than a hydrogen atom, and a magnesium atom is twice as heavy as a carbon atom. In other words, 12 hydrogen atoms would have the same mass as a single carbon atom, and 2 carbon atoms would have the same mass as a single magnesium atom. Or we would need 24 hydrogen atoms to have the same mass as a single magnesium atom. Now here's the important bit. This means that if I have equal numbers of particles of all 3 elements, the carbon atoms will have 12 times the mass of the hydrogen, and the magnesium will have 24 times the mass of the hydrogen, and twice the mass of the carbon. This is simply because of the relative masses of the individual particles. If one particle is 12 times heavier than another particle, then the same number of particles will always be 12 times heavier, and so on. For example, 100 carbon atoms will be 12 times heavier than 100 hydrogen atoms, and 1,000 magnesium atoms will always be twice as heavy as 1,000 carbon atoms. What if we consider the reverse? Rather than having the same number of particles of these elements, we have equal masses of these elements. Well, in that situation, if we have an equal mass of hydrogen and carbon, since one carbon atom is 12 times heavier than one hydrogen atom, then we have to have 12 times the number of hydrogen atoms to make up the same mass. Similarly, if we have an equal mass of carbon and magnesium, then we will have to have twice the number of carbon atoms than magnesium atoms, since each carbon atom is half as heavy as a magnesium atom. If I had an equal mass of magnesium and hydrogen, then I would have to have 24 times the number of hydrogen atoms as magnesium atoms, and so on. We could also say at this point that if we randomly take the atomic mass number of grams, that is 24 grams of magnesium, 12 grams of carbon, and 1 gram of hydrogen, then they will all have the same number of particles, since the ratios are the same. But we'll come back to this shortly. So now we have a way of comparing the mass and number of particles between elements. We chose the elements hydrogen, carbon, and magnesium here because their simple ratios make it easier to understand, but we can actually extend the same principle to all the elements in the periodic table. The ratio between their relative atomic masses tells us what mass we would need to have of that element to have the same number of particles as any other element. For example, there are the same number of sodium atoms in 22.99 grams of sodium as there are hydrogen atoms in 1 gram of hydrogen. There are the same number of sulfur atoms in 32 grams of sulfur as there are carbon atoms in 12 grams of carbon or hydrogen atoms in 1 gram of hydrogen. There are the same number of krypton atoms in 83.8 grams of krypton as there are magnesium atoms in 24.3 grams of magnesium, or hydrogen atoms in 1 gram of hydrogen, or carbon atoms in 12 grams of carbon, or indeed osmium atoms in 190.2 grams of osmium, or radium atoms in 226 grams of radium, and so on. As the elements get bigger and heavier, you need an increasingly larger mass to have the same number of particles. So now we have a system. For any element, we know that the atomic number in grams will contain the same number of particles as any other element's atomic number in grams. Indeed, we can extend this further to compounds and molecules, where the formula mass in grams of a compound contains the exact same number of molecules as the formula mass in grams of any other compound. And 3 guesses for what we call this. In other words, the atomic mass of any element, or the molecular mass of any compound in grams, is 1 mole of that substance, and will contain the same number of particles of whatever that substance is made up of as a mole of something else. The particles might be atoms or molecules or ions or whatever. It doesn't matter. We know we will have equal numbers of those particles if we have the same number of moles of anything. For example, 1 mole of carbon dioxide will contain the same number of molecules as there are carbon atoms in 1 mole of carbon. Now, at this point, it becomes useful to know how many particles that actually is. How many actual atoms of carbon are there in 12 grams of carbon? Or how many actual atoms of magnesium are there in 24 grams of magnesium? Well, it turns out when you do the experiment to find how many particles there actually are in 1 mole of something, you get 6 by 10 to the 23. An insanely large number. But there you go, atoms are small. We call this number Avogadro's number. The number was not discovered until long after Avogadro had died, but it was named in his honour, as he was the first to suggest this idea. And this is all a mole is. It's just the number that we came to use because it happens to be the number of particles in any element's relative atomic mass measured in grams. And it makes our life much easier to be able to read a mole of different substances from the periodic table and know that we have the same number of particles of each. In practical terms, as we shall see, Avogadro's number is a conversion factor. In the same way we count socks in pairs, or eggs in dozens, or paper in reams. Rather than saying 12 socks, we would say 6 pairs. Rather than saying 36 eggs, we would say 3 dozen. Or rather than saying 1,500 pages, we would say 3 reams. It's the same for moles. Rather than saying 6 by 10 to the 23 of some type of particle, we would simply say 1 mole of that substance. Or rather than saying 1.2 by 10 to the 24, we would say 2 moles, and so on. And what mass would the 2 moles have? Well, that will of course depend on what the substance is, since every substance has particles of different weights. A dozen eggs does not have the same mass as a dozen socks, just because I have a dozen of both. Moles tells us how many particles we have. How heavy they are will depend on how heavy each individual particle is. But we will see more about this in topic 6.1, where we will look at conversions between moles and mass. Moles then help us to convert impossibly large numbers of particles to masses, which we can conveniently weigh on a mass balance in the lab. We have this approach because a chemist could not effectively carry out chemical reactions if he cannot count the number of particles he is reacting. He would just be guessing the amounts, and chemists, uptight creatures that they are, do not like to guess. That's it for section 4.2. Have a go with the questions.